Hello, welcome to lesson 34, the development or history of the periodic table and Bohr diagrams. Now this is a fun lesson. There's a lot to do and it kind of becomes repetitive at the end of the lesson, but in a really fun way. You're going to have to do a little chart and then some diagrams as your assignment. Now, I want to get into something quickly just to make this one a little bit easier. Now, in the notes and in the reading, especially with the questions you did, you were getting a taste of this. So now we're going to actually get really into it. But before we do that, I just want you to understand a couple things here. Look at your periodic table for a second, right down here. I want you to understand something here. Okay. For example, beryllium, 4 and 9. You need to understand what the difference here is. This is called the atomic number. This is called the atomic mass. And those are the two things you're going to look at the most. Now, what you need to understand is the atomic number. I'll put it up here. You don't need to write this down because you're going to get a lot of practice. But the atomic number equals, it's the bold one, and equals the number of protons. Now wait a second. If I know the number of protons, I also know the number of what? Electrons, right? So if I say here, 4 is the atomic number, that means that beryllium has 4 protons. I also then, using my brain, can realize that beryllium also has 4 electrons. Okay. So 4 protons. I'll put and electrons. Right? Because we just know that. And this is called the atomic mass. Equals, now what does the atomic mass equal? Equals protons plus neutrons. Oh no. So what does that mean? Well, think about it this way. If this tells me that the atomic mass is 9, and I know that there's 4 protons, how many neutrons must there be? I would take 9 minus 4 equals 5. So now taking this number and subtracting that, I have found out the number of neutrons. You're going to have to figure out the number of protons, neutrons, and electrons of every single element for the first 20 or so. So you need to understand that. How do I find out how many protons? I look at this. How do I find out how many electrons? Well, I look at this too. How do I find the number of neutrons? I have to take the mass and subtract the number. So for example, if I looked at magnesium, there's 12 protons, which means there also must be 12 electrons. How many neutrons would there be? 24. Don't worry about the decimal so much. Don't worry about that. 24 minus 12 equals 12 neutrons in magnesium. If you understand that, when we get to the later part of the lesson, it's going to be a little bit easier. So that's just a little crash course, and you're going to get a lot of practice doing it. So don't stress it. I'm going to help you out. All right, now let's move on to our main lesson for today, discovering how they worked on the periodic table and created it and started organizing it. And then we're going to look at Bohr diagrams, and you're going to be drawing a lot of them. This is lesson 34. Let's take a look. So there is our periodic table, but how did they organize it? Why are all these things in this? Why are these here? Why are these all in these different rows? What's this? Why are they color-coded? We're going to start getting into that today. So, in the way back day, right, Dobereyer and Newlands in the 1800s, they both observed that the atomic masses of elements seem to be related to their chemical properties. So they realized, sort of, if you look here, the atomic mass, that these numbers, so the weight, protons plus neutrons, seem to have something to do with how things reacted. They couldn't organize it, but they were like, as things get heavier or lighter, if we look at that atomic number, the protons plus neutrons, there seems to be a pattern. We couldn't figure it out. Meyer in 1865 proposed there was a repeating pattern of properties. So you'd go up to a certain thing, and then it would reset the way they behaved, so you'd start again here. So you can see back here, right? Repeating pattern, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So why did they go from 18 to 19? Because these behave a certain way. So every time you would test a chemical and it behaved a certain way, you'd just go back to the first row. Don't worry, we'll get into it a little bit more later. And then Mendeleev. He placed the elements into an organized table, and he's the guy you need to know. So Mendeleev is the guy to understand about organizing these, right? So he put the elements into a table. He stated that the property of elements are a periodic function of their atomic mass, and this relationship is called periodic law. Okay. Mendeleev, what he's known for, is arranging 63 elements known at the time in order of their atomic masses, so the elements with the same valence electrons appeared in the same row. Now, I just want to see if I could find this. I wasn't planning on this, but let's see if I can look up here. Mendel early periodic table. Let's see. Is there a picture of it? This is what he made. Okay, that's kind of cool. So you could see what he invented up here. That was the best he could do. Of course, this was in the 1800s, and they didn't even have the technology to confirm any of this. But he was already kind of building a periodic table before we knew all the elements that we know today, or we knew how to exactly identify them. He was already trying to organize them. And he said it was a repeating thing. You could take the mass, and then a new would behave a certain way, behave a certain way, behave a certain way, behave a certain way. And then all of a sudden, you get to the next number in atomic mass, and it would behave like the first number again. So he'd restart the table, which I think is kind of cool. So back to this. He arranged those 63 elements in the order of their atomic masses. That is very important. We organize, right? He used atomic mass to organize his. Nowadays, we use, and this is a difference, right? We use atomic number, right? We use this to organize. He used this. And you'll see there's some differences because there's some times where these numbers don't actually flow in the right order. There's some right here. Look at this one. 63. Oh, sorry, that's the wrong one. My bad. But there's some here where the number before will be higher. Don't worry about that just yet. We'll look at it later. But we use atomic number. He used atomic mass, and you need to understand that. He found that there were vertical columns that contained elements with similar properties, which he called families or groups. So he realized that there was vertical columns going up and down this way, right? Going this way. And they behaved right over here, same thing. They behaved in the same way. Everything that was in that vertical column, so he called those families. And we're going to have to learn this family, this, etc. We're going to learn all these families in the next lesson. But he was the first one to start grouping them like that. Not all elements had been discovered at that time. Once Mendeleev had established a pattern, he left, this is so cool, he left spaces for undiscovered elements. How genius is that? How creative is that? How optimistic is that? I know that I don't know everything, but there's things in my theory that don't work out, so there must be elements we haven't discovered. So he would kind of get this far, and then the next thing might behave like this. So he would leave spaces in his table because he knew he would discover new elements later. He left spaces for undiscovered elements, correctly predicting that elements would be found to fill the spaces. Mendeleev's periodic table was instrumental in the discovery of 23 new elements in 30 years. Just by him leaving those spaces, it inspired physicists and chemists and scientists to go and find other elements. There must be one. If this one is 10 and this one is 14. There must be one with 12, right? Oh, he got this and he got that. There must be something. And people started filling in the table by finding new elements that behaved or weighed the right amounts to fit into his table. And we started creating a better and better version. Science is amazing. Let's move on. All right. Moseley stated that physical and chemical properties are connected to their atomic number. So that's the big thing about Moseley. Moseley said, okay, Mendeleev, you were using the number on the right. You're using mass. Back it up, buddy. I think you need to use atomic number, the number of protons and electrons. So he was kind of a groundbreaker, and he kind of reinvented what Mendeleev did, but he said instead of using atomic mass, which is protons plus electrons weight, we're just going to use, or protons plus neutrons weight, we're just going to use atomic number. So instead of using this number, we're going to organize things by that number. And look at how beautifully that free flowed. 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. It works perfectly now. So this explained the gaps in the table better, and he created the modern periodic table in which each element has one more proton than the element before it. One. They put it over here too, if you can see. They also repeat hydrogen there. 2, 3, 4, 5, 6, 7, 8. So his big claim to fame, if you need to know, you might want to star that or circle it or highlight it, but he used atomic number rather than mass. That was his big contribution if you're ever asked on a test or a quiz. All right. Periods. Okay, what is a period? A period is a horizontal. And that's all you need to know for now. So if I'm talking about a period here, this is a period going this way, right across the top. This is a period going this way. This next row is a period, a period, a period going across this way. All right, so that's okay. Each period number represents how many electrons or shells. Now this, pause, right? You don't know this yet. We're going to do this in the next part of this lesson today. But you need to understand that each period number, so period 1, period 2, period 3, period 4, period 5, period 6, etc. Each period number represents how many electron shells they have. Remember when I talked about an atom looks like this, right? You have a nucleus, and then you have shells of electrons, which is what we're going to be doing today. Well, in this period, period 1, right here, there's only going to be one ring. In period 2, when we're drawing these diagrams, there'll be one ring, two rings. Period 3, right here, right, period 3, there would be 1, 2, 3 rings, 4, 5, etc. So that's what period means. You need to know that. Period represents how many electron shells. Okay. But what about, Mr. Sitnick, what about these? What about, if we know this means how many rings there are, how many shells there are, what do these mean? What do these vertical columns mean? We'll get to that right now. Let's take a look. Groups are families. Vertical columns on the periodic table. So this is considered a period going this way, and this is considered a family or a group. All right. A new numbering system numbers them 1 to 18. We used to use Roman numerals, and you can see there are Roman numerals in the middle, so we use both. We put the number 1, 2, right? Groups contain elements with similar chemical properties. So everything in this group chemically behaves very similar. Very reactive, not as reactive. Very, very, very not reactive. Not that reactive, a little more reactive. Very reactive, right? Extremely reactive. So depending on each column, each vertical column, it actually shows how they're chemically similar. Elements of a group have the same number of valence electrons. Don't worry about that yet because we're going to get into it, but you need to know what a valence electron is whenever you look at a diagram, the last ring is always called, so if we did one that only had one ring, well, this would be considered the valence ring. If we did an atom diagram that had 3 rings, well, the last ring is considered the valence ring. And how many electrons are in that last ring, and we haven't learned that yet, how to do that, but what you need to know is that this family all has 1 valence electron, 2 valence electrons, and then we jump over the middle, the gap, 3, 4, 5, 6, 7, and then a full ring here. So that's what those mean as well. Rules for chemical symbols on the periodic table. The symbol is usually the first 1 or 2 letters of the name, generally speaking. Sometimes the old Latin name is used. For example, Pb for lead. That's Latin for plumum or plumber. Lead, because plumbing used to be made out of lead. That's where the name plumber comes from. Pb, plumber, lead. We don't use Ld for lead. We use Pb because that's the old Latin name. The first letter of a symbol is always a capital letter. The second letter is always a smaller case. And every element will have a different symbol. Those are some of the rules of thumb for looking at a periodic table. Now, you could do this yourself. Look in your periodic table and find the symbols of the following elements, and then find out if it's a metal or a non-metal. You don't need to do the metal or the non-metal part right now. Just look over this and see. Okay, copper, what would copper be? Oh, copper, Cu. Okay, iron, oh, what's iron? That's a tough one. Iron, is it I? No, iron isn't I. Look, I there is iodine. So that can't be iron. What could iron be? So you're going to have to read. Oh, look at Fe, iron. And magnesium, chlorine, carbon. You could find those yourself. I'm not going to spend a lot of time on that, but that's just something for you to do right now just to get comfortable with the periodic table. So you can pause it and do that quickly if you'd like. Now look at your periodic table and find the name that corresponds to the symbol. And you could pause this again, and you could do that if you like. Magnesium, carbon, what are these ones? Potassium, bromine, aluminum or aluminium, things like that. Pause the video if you'd like, and you could do that as well. All right. Now, you should be looking at this page. And some of this page here is review, but this is going to get us into drawing Bohr diagrams. So let's take a look at this quickly. This is almost like the second part of the lesson today, because this is where we're getting to the fun stuff. All matter is made up of molecules. These molecules are small, but they're made of smaller things called atoms. That's all review. Each atom has its own unique qualities. However, all atoms have certain things in common. Atoms are made up of subatomic particles. The arrangement of these particles is called atomic structure. No problem there. Protons and neutrons are found in the nucleus. We know that. They are the heavy parts. That's important. Protons and neutrons are heavy. 1 or more electrons are in orbit around the nucleus. It is almost weightless. Protons have a positive charge, electrons have a negative charge, neutrons have no charge. Atoms always have equal number of protons and electrons. Now, when we're going to draw a Bohr model, you need to be able to find these things. What's a Bohr model? A Bohr model, I'll show you down here, is something that looks like that, and we need to draw those for every element for the first 20 of them. So we got to draw them. To draw a Bohr model, you're going to need to know these things and then create a chart out of it. And don't worry, I'm going to help you a lot on this. We're going to need the number of protons, and we're going to need the number of electrons, and we're going to need the number of neutrons. So to find number of protons and neutrons, for example, look at this one here. They did calcium. Here, I'll keep that in here, actually. I'll put calcium there. Oh, and I'll turn this off. So here they do calcium. All right, so I'm going to jump around a couple pages here. All right. So what do you need to know? You need to know the number of protons, the number of electrons, and the neutrons. How do you find protons? Let's look at calcium here for a second. Calcium right there. How do we know the number of protons? Well, we just look at the atomic number. There's 20 protons. How do we know the number of electrons? Well, guess what? Protons and electrons, because it's positive and negative, they have to balance. Otherwise, you'd have a crazy, weird chemical element that would be reacting stupid. So you have protons and electrons. We know that just by looking at that. So there's 20 protons and there's 20 electrons in calcium. We know that already. Now, how many neutrons are there? Well, we have to take 40 minus 20. Well, that one's really easy. That's not a fun one to start with, but there's 20. So we've learned here, as you can see in the diagram, that there's 20 protons, 20 electrons, and then we obviously did 40 minus 20 to find out there was 20 neutrons. And then we create a diagram like that. Now don't worry, I'm going to show you how to do that now, but you just need to know how to, when you look at any element on the periodic table, you have to be able to look at those numbers and say, how many protons, how many electrons, how many neutrons, and then you can draw any one of these as we're going to do right now. All right, so that's how you figure those out. That's very important. Let's take a look. Here's some rules for putting your electrons in those shells like we show you here, right? Some of the rules. Electrons are found outside the nucleus, but they are not just floating around. The electrons are located within electron shells. There are 6 shells that we can learn, and we're not going to really use all 6, but you should know them. In the first shell, you can put 2 electrons. In the second shell, you can put 8 more. In the third shell, you can add another 8. In the fourth, 18. Fifth, you can add 18 more. And sixth, don't worry if you don't understand that yet. I'll explain it right now. All right. So let's look at our friend calcium. How did we get that? Here's your first example I'm going to draw for you. All right. So we knew we're going to say calcium. And I'm going to draw this diagram for you now. Protons equal 20. Neutrons equal 20. Electrons equal 20. Okay, so I've got to put those in a chart. So the first thing I do when I draw a Bohr diagram is I always draw the nucleus. And I'm going to say how many protons. And I'm going to say how many neutrons. No, they won't always be the same. We just happen to have one this time that is. Then I have how many electrons? 20 electrons. I must place 20 electrons. Okay, so in the first ring, I draw. How many can the first ring hold? It can only hold 2. So I can get rid of 2. So I can put an electron and an electron. No problem. But how many? If I've got rid of 2, how many do I have left? I still have 18 left that I got to put. How many can the second ring hold? It can hold 8. So I can get rid of 8 more. Okay, I'll do 1, 2, 3, 4, 5, 6, 7, 8. I have placed 8 plus 2, 10, which means if I started with 20, I have 10 more to place. Okay, so I have to do another ring. How many can the third ring hold? 8 more. 1, 2, 3, 4, 5, 6, 7, 8. I have placed 18 electrons, which means I have 2 more. Can the next ring? Oh, it can hold 18, so there's no problem there. So I can just draw the last one, and I can draw 2 electrons there. That's how you come up with this diagram here. You put the protons and neutrons in the middle, and you put the electrons in rings depending on how many. And remember, it's 2, 8, 8, 18, 18, and 32, depending on each ring. Now, what is that last ring called? That last ring is called last ring equals the valence ring. So how many valence electrons do I have? How many electrons do I have in the last ring? So valence electrons, 2. You'll notice something cool in the periodic table as you get better at this. Everything in this column has 1 valence electron. When you draw it out, everything in this column will have 2. Skip the middle. We don't really pay much attention to the middle. Everything here will have 3 valence electrons, 4, 5, 6, 7, and then this one doesn't always have 8. It always has full. So whatever the max is for that ring when you're drawing it, it will always be full. Kind of cool. All right. Now, a little bit more in your handout. All matter is composed of atoms. Atoms cannot be created or destroyed. This is important. This is called atomic theory. This will be the rules of atomic theory. And you can look at that. That's all stuff there. Now here is your first assignment for the day. I want you to do some math. So, number of protons, 7. So we know protons and neutrons. Protons and electrons are always the same. So how many neutrons are in the atom? Well, we have to find number 7. We have to look at our table. Okay, 7. 14 minus 7, so we could say that was 7. What is the atomic mass? Well, that is this number, 14.01. Okay, the atomic number of the atom, that's this number here, 7. The element's name is nitrogen. And the chemical symbol is N. Then you can do the next one. Oh, this one says 5, so I find 5. We're talking about boron, so I can write that right now if I want. Boron, Mb. How many neutrons? It says 6. How did they get 6? You go to boron, you take 10.81 rounds up to 11. 11 minus 5 would be 6 for neutrons. The atomic mass would be this number here, 11, or 10.81 realistically, but I just put 11. I'm getting a little lazy. And the atomic number, well, that's just this again, 5. So your first assignment is to go through and fill this all out. This is the hard one to understand. That's where you have to do the subtraction. You don't need to do this one. Don't worry about that. And then I'll just do an example here for you. Let's see. Here is a Bohr diagram for beryllium. All right, let's see. How did we figure that out? You always put protons and neutrons in the middle. Let's look at beryllium. Protons is going to be 4. Neutrons is going to be 9 minus 4 equals 5. So let's see. 4 protons, 5 neutrons. I draw that in the circle. Then how many electrons did I have to get rid of? Well, if it's 4, I have to put 4 electrons. So I have to place 4 electrons. So the first ring can take 2. So I draw a ring and I put 2. And that means I have 2 left over. So in the next ring, I draw 2 more. And I could say valence, which means the outer shell equals 2 out of 8 possible that it could hold. Cool. And let's look at one more. Let's look at potassium. And you can pause it if you need to. But potassium here is K. All right, let's look at that. Okay, K, get it? Now we know since it's in this family, it's going to have 1 valence electron, but how can we prove it? Okay, so we know the protons and electrons is 19. Protons, electrons, 19. We're going to have to place those, right? We're going to have to place them. And neutrons, how do we figure out neutrons? 39 minus 19 equals 20. So in the middle, we draw 19 protons, 20 neutrons. We have to get rid of 19 electrons. The first ring can hold 2, so I put 2. The next ring, I can put 8 more. So I put 8 electrons in the second ring, so I've gotten rid of 10. The next ring can only hold 8, so now I've gotten rid of 18 in total, which means I have 1 more electron. So I put 1 more ring, and I put there, and I say the valence equals 1 out of 8. And is that in line with what we said here? Because I said everything in this will have 1 valence electron, and of course, potassium is there. 1 valence electron. And since it's the 1, 2, 3, 4th family, do you think that there's going to be 4 rings? 1, 2, 3, 4. That is pretty cool. Your assignment today is to take the periodic table and draw Bohr diagrams for 1, 2, 3, 4, 5, 6, 7, 8, all the way till 18. Skip the middle, obviously, but do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Draw those Bohr diagrams on a piece of loose leaf, on a piece of paper. I've done a couple for you here. Submit those along with the picture of this chart that you did, right? You don't need to do the bottom. So submit this and Bohr diagrams for the first 18 elements in the periodic table. Submit those to lesson 4, and we'll see you soon.